All right. This lesson is going to kind of catch a number of different things. We're going to talk about different ways of representing these relationships between inputs and outputs and how to get from one to another and visualizing certain things. So may not look totally like it all goes together, but it does. All right. So first one we're going to look at is a graphs and stories connection here. The story is that the sales at a souvenir shop in Seaside are high on spring break and over the summer, but they're pretty low the rest of the year. We don't have any exact numbers on here, but if we let this, and we're going to kind of sketch a graph here, and this will be our sales at 0, and this will be over the course of the year. Spring break, we'll maybe say spring break is happening about there. And then summer, maybe all of this is considered summer in that gap in there. So we're not shut down. We are making some sales, and maybe coming off of New Year's and stuff, things were okay, but they come in here, and then right around spring break, there are a bunch of people are in town, so the sales spike for a little while, and then they drop back off as people take off, and then summer comes and there's people around the summer and they're happy and they're buying stuff, and so maybe the summer looks something like that, and then it kind of drops off through the course of the year again. They maybe get again a little bit of a lift around Christmas, so a graph might look something like that. And where this again is the time over the course of the year, and this is the sales going in that direction. Okay. It's a little bit different one here. This next one, we've got a vase here, and we're going to fill the vase with water, a steady flow of water. And we want to sketch a graph of the depth of the water in the vase as time passes. I've tried to line the vase up with the bottom here, so when we first splash water in, right, it's kind of curved there at the bottom, so it might fill up fairly quickly and get a level there, but then it gets pretty wide, and the wider it gets, the slower the level is as it's going up, the slower the level's moving, and as it shrinks back down, then it kind of starts to pick up the pace again. So we'll see what we can do here and hopefully not run out of graph. So starts out, the level climbs fairly quickly for a little while, and it's going up there fairly quickly, but then it's constantly going up, but not as fast, and it gets particularly slow at that widest part right there. And then it starts to pick up again a little bit because the thing's a little bit skinnier, and then we hit that skinny part in the middle, and that climbs pretty quickly right there, but then things start to slow down again a little as we move through there, and it gets fairly slow, but then again starts to pick up, and the last little bit is nice and quick because it's fairly narrow there again. We imagine that hollow sound you hear when you're filling something up like that. Okay, so it's not an exact graph, but maybe we can see how we believe that has something to do with the way that water level rises in there. It's not like just a cylinder where it's going up at a steady rate, but that rate that it's climbing changes over time. So this is the time again here, and this is the water level. Okay, this is one that definitely has that idea of a domain and a range. As the water's filling, it doesn't make any sense to go past this. Once we've gone over the top, the level's not going to go up anymore. It's overflowing, so it definitely has a range that has to do with exactly how tall this thing is, and a domain that has to do with the amount of water that's coming out of there until we reach the top of the base. Okay. All right, let's look at stories to actual equations. We couldn't really come up with an equation necessarily for that one. So the story here is we've got a rectangular piece of cardboard that's 20 by 30. This is probably not exact dimensions, certainly not exact dimensions. We're going to create an open top box out of this by cutting squares out of the corners. So we're going to cut a square out here that is X inches by X inches, and exactly the same size square out of every single corner. And then if we came across here and we fold on that line, and we fold on that line, and we fold on this line, and we fold on this line, those corner pieces are gone. And everything folds up and makes a nice open top box for us. Okay, so let's experiment here a little bit. Let's pick some different values for the X. Maybe we fold 2-inch by 2-inch squares. Well, if it's a 2-inch by 2-inch square, and this whole thing we said was 30 inches long, and this is 20 this way, well, from that 30 inches, I took 2 inches, I'll do that in a different color so we can see it. I took 2 inches out there off of the 30 and another 2 over there. So that's actually down to 26 inches long now. And we took 2 inches here and 2 inches here. So this piece left in the middle that's going to be that side of the box is going to be 20 minus 4, or a width of 16. And so the volume, since the box is length times width times height, so 2 times 26 times 16 is going to give us a volume of 832 cubic inches. Okay. All right, let's go 4. Shall we do 4? We'll do 4. Okay. Nobody argued with me, so. If we go 4 inches on each of the squares, then we're taking 8 inches off this long side, and so the length is going to be 22, and the width, 4 inches off of that top part, and 4 inches off of the next part, 8 inches off of the 20 leaves 12 inches there. And so we could calculate the volume. That's 4 times 22 times 12. That's 1,056 in the volume. Okay, so can hold more stuff in the box if we do that. Let's try something else. Let's go with 8. Okay, we'll try an 8. Or 7, so you don't think it has to only be even numbers. So if we go 7 on each side, then that's taking 14 off of the length, which leaves 16 left over for the length. And on the width, we're taking 14 off of that as well, which leaves us 6 on the width. Okay, so a little bit taller box, 7 times 16 times 6 is 672. So we started out with a fairly small square and ended up with a volume of 832. We made the square a little bit bigger and we got 1,056, and we made the square bigger than that and the volume started to go down again. So let's see if we can generalize this and say, well, what if we cut out in inches? Well, the way that we found the length every time was we took the overall length, which was 30, and then we subtracted 2 times whatever the x was, so 2 times n. 30 minus 2n will be the length, and 20 minus 2n will be the width. And so the volume is these 3 numbers multiplied together. So that's n times 30 minus 2n times 20 minus 2n, which is looking very polynomial. We could certainly multiply those things together. I want to take a look at that actually in Desmos. We will graph that thing. So we'll graph y equals, and we can put it in exactly the way we had it. I'm going to use x's instead of n's. 20 minus 2, I guess it was 30 minus 2x. And 20 minus 2x. Okay, and that's a little bit hard to see. Okay, so we'll probably, let's zoom a little bit here. We've got 3 x's, so expect that it will be a cubic, and we have an idea what our cubic looks like. Let's try to adjust this a little bit, maybe make our x's go from -1 to maybe 18. We can see a lot more of it. Our y's, those are going way up there. We knew we had that one that was up there close to 1,000. Let's go down here to and see what 1,500 does for us here. Okay, we can kind of see the interesting things that are happening in the graph there now. Okay. And so what kind of information can we get from this graph? Well, if we were interested in just how big we could make that box, if we wanted the largest possible box, okay, this is volume on the y-axis, and so this is going off to infinity over here. The problem is that to make what it calls an infinitely large box, we would have to chop squares out that are more than 15 inches. But if we try to do more than 15-inch square, we're completely out of box. So the domain of this problem is actually just 0 to 10. So we get this graph that tells one story, but when we look at the actual story on the thing, we understand that we can either cut no squares out, and then it will hold nothing because it's just a flat piece of cardboard. Or if we cut out 10-inch squares, then we've taken all of the width out, because that's we'd have no width left, and that would be just a flat box again. So it's only between those that make sense. And this one says up here that the best you can actually do is to cut squares that are 3.924 by 3.924 out, and you will get a volume of 1,056.306. Okay. All right, so that, I just wanted to throw that extra thing back in there. All right, so we can build the model this way. We actually were able to come up with an equation by kind of following a pattern along the way there, and then using Desmos to come up with the best possible answer. That 4 was actually very good. Okay, in terms of whole inch numbers, and even to the nearest quarter of an inch, it looked like that was going to be the best one. All right, another way that we can create this relationship is, and we're going to use Desmos again, and we're talking about a regression. So we've got data that we've gathered from an experiment in a table, and we're going to take a look at, and we're going to scatter plot it, take a look at what it looks like, and then try to find an equation that goes through there. Okay, so some notes that you can write on here as we go are how to enter a table into Desmos. And if the table data you have is in a spreadsheet, you're able to just copy and paste it right into Desmos. It's super cool. I don't have that available to me right now. And then you'll write down some notes here about how to create a regression equation as well. So I'm going to demonstrate using this data. So back into Desmos here, and here's the first note to enter a table in Desmos. we want to hit the little plus sign and say put a table in there. It automatically labels that table with an X1 and a Y1. We can change those names, but it's really handy to have those particular names in here. So I'm going to put the data in that was in the table, hopefully correctly. All right, and there is what I see if I am a diehard Coug fan and I don't want to see purple on my screen, then I can change that to a different color. Okay, I'm going to hide this other equation up here so that I don't have to look at that in there. And I see this shape. Well, what Desmos allows me to do is try a number of different types of equations. Okay, this looks like, it definitely doesn't look like it's trying to be a straight line. It doesn't look like it's trying to be exponential. Of all the things that I know, it's some kind of polynomial here. And so what I do is I type y, and if I type a 1 right after it, it'll automatically subscript it for me. And then I want a tilde. The tilde says, I need Desmos. Desmos, I need you to go in and find this for me. And so what do quadratic equations look like? Well, we had a few different forms, but one of them was ax squared plus bx plus c, and all I have to do is make sure that when I say x, that I make it the x1, so it's referring to the one that was in the table, plus bx1, it's not looking very good so far, plus, okay, when I put the plus c in there, then suddenly it looks really good, okay? And what Desmos is telling me here, I'm going to take this information and put it over in our other document. So this is the information that I got from Desmos. And I stopped there because it looked good. If I had tried, you could see what was happening when I just had ax1 squared, didn't look anything like it. The bx1, not even close. But this down here tells me the values of b that made that fit the way that it did. Okay. So to enter a table in Desmos, we hit the plus sign. We either paste it in or we hit the plus sign, which you can do from some spreadsheet programs, or hit the plus sign and choose table, and then enter the data into the table. And the key in the regression is to use the subscripts and the tilde. Okay, so this is what it needs to look like if I'm doing a quadratic. If I was doing a linear equation, I could do y1 tilde m x1 plus b, and it would tell me what the m and the b are. I can use any letters in there actually that I want. And this one tells me that my equation that fits this data the best looks like y equals about 2.12, read it, I just can't say it apparently. 2.128, 129 if I'm rounding. So 2.129 x squared minus 6.07 x plus about 5. So that is a reasonable fit for this equation. You could experiment and go in there. If you remember our other form, y1 approximate or tilde a parentheses x1 minus h squared plus k, you could do it that way as well, and it would give it to you in the vertex form. So that's looking at lots of different representations, symbolic, tables, we've got graphs, we've got words, in there, and how we should be able to get from one of those representations to any other one of those representations.